Okay, so good morning. So today we finished the last part on compact operators, and for symmetric operators we give the decomposition, and then we start with some exercises. So if you have some specific questions, otherwise I choose some exercises which are, well, in my opinion, good exercises, and they will reflect what you get in the written exam. I'm sorry I did not have time to prepare the sample for the exam. I will do it later. So let's recall what we are doing now. So it is the spectrum of compact operators. Okay. And okay, what we reached last time was that, well, due to the several properties, so basically it is a result, let's say it is theorem, that, well, the spectrum of T is contained in the complex plane, let's say, in the lambda, such that modulus of lambda less than the norm of T. And if T is compact, okay, now we know that 0 belongs to the spectrum of T, and okay, E is infinite dimensional. Zero belongs to the spectrum, and then the spectrum of T minus, okay, what is 0 is made of eigenvalue, is the point spectrum, is, okay, is contained in the point spectrum of T. So you have only eigenvalues, and actually the spectrum of T minus any ball of radius rho around 0, so in the complex plane, is finite. Okay, so you have finitely many eigenvalues with norm greater than 0. And okay, what we were doing last time is okay, very similar to the analysis. I don't know this guy. For if the compact operator is symmetric, so symmetric compact operators. Okay, and symmetry, I just recall that symmetric means for general operator means that the adjoint is equal to T. And okay, but be careful because for unbounded operators, symmetric and self-adjoint are two different notions because the domain may be different. So if it is bounded, it's defined everywhere, and I don't have any problem. Okay, so in that case, well, you have to think always to the finite dimensional case, which gives you the test bed for the result that you can prove or you cannot prove, or that you can hope for or not. So the T star equal to T, let me recall that it means that TU V is U TV. Okay, because being T, it requires to be in a Hilbert space, because otherwise it's meaningless. And so, for example, if you have matrices from Rk to Rd with k different than d, then okay, the adjoint, yes, is defined, but cannot be said equal. So they should be in the same space, and this relation hold. Sorry, TVU. Oh, yeah, was correct. Oh. Okay, so what the last statement we had was the following proposition. That is, let me say, okay, this is for general stuff. So T symmetric or self-adjoint, but symmetric, let's say, in our notation. And bounded. That, okay, the two quantities which are the minimum and the maximum. M is the infimum, TUU, and M is the maximum, okay, the supremum, I don't know yet. So norm of U equal to 1, TUU equal to 1. Okay, if you think to the finite dimensional cases, you know that they give the minimal and the maximal eigenvalue. And that's what we are going to show, more or less. Okay, then the spectrum of T is real. And okay, we are not going to prove it, but because in the book you consider just the real vector spaces, and the spectrum is defined for real numbers. However, keep in mind that this is true in general, and okay, we can prove it. It's not maybe as an exercise. And actually, it is contained in the interval M capital M, as in the finite dimensional case, and the norm of T is equal to the max minus M and M, so which is exactly the one-dimensional case, no? So the finite dimensional case. Okay, so let's restart the proof since 1 week has passed. Okay, the key observation is that by this property, is that, okay, AUV equal to TUV, okay, for real space is symmetric and bilinear. So I would be fine. I mean, I can use all the machinery of the Lax-Milgram theorem whenever it has a sign. So it's positive definite or coercive, depending on your definition. Okay, so in particular, let's start with, okay, in particular, if lambda is greater than m, lambda is a real number, because we are not going to work out this observation. Then lambda minus t, so lambda minus t uv is positive definite. Okay. So now what we have from the Lax-Milgram theorem, well, then, so, okay, Lax-Milgram or whatever you prefer, because there are several ways of doing it. So let's say Lax-Milgram, one, or I just observe that then lambda minus t is a scalar product, which is equivalent to is an equivalent to my original scalar product. So whichever you prefer as a proof, we can solve. So for any f, in H there exists a unique U such that, okay, the scalar product means that I represent any linear functional as the scalar product with a vector. So using this particular form of the vector, I have that lambda minus t u equal to f. And okay, this gives what? This gives that, well, being coercive, it is injective, and being inverted, this ratio it is invertible, so it means that lambda belongs to the resolvent of T. Simply because I can invert it. Given me F, I find a unique U which satisfies this relation. And this is the inverse. Okay. And since it is coercive, I can also compute the norm of U by exercise. I just take I multiply by U, then I simplify, get that is the square root of lambda minus, controlled by lambdas minus m over square root. Okay. So what about the other inequality? So when I take a lambda before here, so if lambda less than m, do you have an idea?
T minus m.
Yeah, one consider T minus m u as a scalar product, uv, as a new scalar product, or as a new coercive bilinear functional, and then you get the same. Okay, so we discover that as in the scalar case, we arrived to this point. Wait, we know that it is contained, but now let me see if I add something. Ah, yes, sorry, I forgot to add that m belongs to the spectrum. Okay, so let's see the other part. Now we want to prove that I have some chalk in my nose. Okay. Now we want to prove that M belongs to the spectrum of T. So as before, we take the symmetry function. So take A uv is equal to M minus T u v, which is again symmetric, bilinear, but is not positive definite now. But in any case, it is symmetric. So, and then we recall that, well, that the Schwarz inequality depends only on the positivity, because okay, Schwarz requires only that is greater or equal than 0, because it's just a linear relation, and then you minimize by a scalar factor. So the Schwarz inequality, so it's A uv less or equal than A uu to 1/2, A vv to 1/2, okay, which gives that M minus T u v is less or equal than, okay, whatever is ident M minus T uu 1/2 N minus T vv 1/2. Okay, so now we take v equal to 1. So the supremum of this guy is so M minus T u in norm. This chalk today is burning my nose. I don't know why. Okay, so this is less or equal than m minus t u to 1/2, and then I keep, and then I look at this guy. So this guy is the norm of v multiplied by m minus t vv, and the maximal, if I go back here, is when I subtract the minima, so the infimum, which is m. So this is m minus m to 1/2. The minimal thing I can do. So now assume un, okay, is such that t un converges to, okay, the supremum, so that's defined, to m. So now in particular, we have that this guy converges to 0. This guy is bounded, so we deduce that m minus t converges to 0. So, but now we reach the contradiction, because if, so, and then we say that norm un equal to 1. Okay. So now if n minus t, okay, is invertible, then I just rewrite the thing. So I write that un is m minus t to the minus 1, and then I have n minus t applied to un. Now we reach the contradiction, because if this is invertible, essentially it tells me that un should converge to 0. So un should converge to 0, which contradicts the fact that I take un equal to 1. Okay. So it cannot be invertible. And so the same thing for the same for lambda equal to m. In that case, you take t minus m, and then you do the same computation. Then you observe that it cannot be invertible, because you have a sequence which converges to 0, but actually does not converge. It cannot converge to 0 by definition. Okay, so the final thing is the estimate on the norm. So norm of t is the max t minus m and capital M. Okay, even here they are quite standard. So again, we use the symmetry. Tu plus v plus or minus v, u plus or minus v. Well, this is like for the scalar product. So it is t u plus or minus 2, and here I use the symmetry t uv plus t vv. Okay, which gives the parallelogram formula for the scalar product, which is tuv. Okay, but you cannot say these guys are norms. So summing up, okay, we obtain that this guy is 4 tuv, or I think I subtracting. indeed is not a parallelogram formula, is the fact that if the parallelogram formula holds, then the norm comes from a scalar product. So is how to obtain a scalar product by using the parallelogram formula. So subtracting is T u plus V minus T u minus V u minus V. Okay, these guys, I take the maximum, so it's M u plus V squared minus M u minus V squared. Okay, and then I do just some algebraic computation, so it's less or equal than 2 times the max, so minus M and M, and this is U squared plus V squared. I choose the one which is larger, and then I use the minus. Okay. So if I look back, then I obtain that TUV is less or equal than, okay, this quantity here, 1/2, the max, minus MM, and then I get, okay, here I can, okay, if I stay here is U squared plus V squared, but you see where I'm going to, no? Since this is a quadratic relation, I just scale things. So in my computation, I get that I can put, so if this I divide by alpha, and this I multiply by alpha, is the same, but here is divided by alpha squared, and this is multiplied by alpha squared. Okay? So take the minimum. The minimum is, if you compute with respect to alpha, you get T alpha V less or equal than is the product. And so the conclusion is that norm of T, taking the supreme with respect to V and then the supreme with respect to U with norm 1 is less than the max. Okay, and this concludes this proof. So the corollary of this property is that, let me say a remark, not a corollary, just a remark, it's okay. So if T is symmetric, self-adjoint, and the spectrum of T is equal to 0, then T is equal to 0. Okay, so with this property in hand, now we can conclude with the last result, which is very useful. Here's the spectral decomposition.
Hilbert-Schmidt theorem.
Pardon?
Hilbert-Schmidt theorem.
I don't know if it is called Hilbert-Schmidt. I know just the name as spectral decomposition. Hilbert-Schmidt, I know this is some result on the operators, which are called Hilbert-Schmidt operators, which are represented as matrices on a base. But okay, it doesn't matter. This I don't know which is the name. I usually
In Russian textbooks, it's called Hilbert-Schmidt.
Hilbert-Schmidt. So H separable. And T compact. And symmetric. Then there exists a Hilbert base of eigenvectors of T. Okay, so essentially I'm saying that, so in the finite dimensional case, just because one loses the stuff, so I'm saying that T E M, let's say E N M equal to lambda n E N M, and then E N M are orthogonal, and the span of these guys is equal to H, the closure. Okay, I need the closure because it's infinite dimensional, otherwise I don't need the closure. So it is exactly the spectral decomposition of five-dimensional matrices up to the fact that I need to take sequences. And
What do we say, Professor, about non-separable space?
pardon? What
do we say about non-separable case? Namely, H is not separable space, but it's Gilbert space. T is compact, self-adjoint operator.
Then we know that for the eigenvalues which are outside, they have the finite range. So you know that you need countably many for the lambda which are non-zero. And then you have the case equal to 0. So it is the kernel of T is an uncountable Hilbert space, take any base. But you cannot write as, well, it's not a countable Hilbert base. So you see outside 0, because of compactness, you cannot have more than countably many things. And for 0, you take any uncountable base. Works.
Thank you.
Okay. But it's not so. So let me say this in the applications, the fact that usually is not very interesting when the kernel of T is not empty, because then you take the quotient. So the real thing is when, for example, you take, for example, in L2, let's say H is equal, an easy example, L2 of 0, 1, and then you want to solve the second, so the operator is the inverse, say, minus the second derivative with respect to x, the minus 1 of, and this is your operator T. Okay, this is not very well specified, so let me specify more. So I have the operator T, so let's say T to the minus 1 would be the second derivative, and it acts on the space. I have to be careful here. So let's say, well, this is one-dimensional, so it's easy. So, so let's say T of F is a G such that G0 equal to G1 equal to 0, and G second of X is equal to F of X. Okay, so this is a compact operator because, well, you can have an explicit formula, and then you see that this guy over here, the first derivative, for example, is 1/2 Holder, and okay, because of Holder inequality, and then it is compact by Ascoli-Arzelà theorem. So T is compact. On the other hand, if T of, let's say, F is equal to 0, okay, if you look at, TG. Sorry, I'm saying, yes, okay, G second is,
yes, TF.
Is the G. No, T of f, yeah, is equal to 0. Okay, it's
2
correct.
times integration.
It's correct. I'm taking the inverse.
Walter operator, I think it's.
Yeah, if Tf is equal to 0, okay, then you look, it means from this derivative that f is equal to 0. So the kernel of T is just 0. However, it's self-adjoint because, okay, it's the by integration by part, no? The f, let's say f prime, okay, by definition is what? Is a function g, so I can just write this is the integral of Tf x, which is g, and then I have f, and then, okay, if you do the computation, so if I integrate, I find a function h such that th is equal to my f, sorry, function h such that tf is equal to h. So this means that f is equal to h second. So this is what? Is g, h second, and then you integrate by part. And if you integrate by part, this guy, you get exactly first the minus g prime h prime because of the boundary condition, and then you integrate again, and then you get with the plus g second h prime, which is equal to, this is f, and then you have h by definition is tf prime. Okay, so now by the decomposition, so I know it is symmetric, it is compact, so I can apply the theorem. I need just to look at eigenvalues. Okay, so we need to solve. So this relation, if you observe, is g second. So I need to solve, let's say, Tf is equal to lambda f, but Tf is equal to g. So, and f is the second derivative, so I have g equal to lambda g second. With the boundaries equal to z, to
0.
u1 equal to 0. Okay, and then if you, because of the things, what you get here is the sign. Well, you have the sine and the cosine, but because of the boundary, it is sine of k pi x. So the base, well, up to normalization. Is the Fourier transform, or the base for the Fourier transform, because of the space that I assume, so it is with 0 conditions on the boundary. Okay, so after this example, this is a very fundamental example. So let's see the theorem now. Okay, so everything is done because we know that outside 0 we have only eigenvectors, and we know that from the remark down there, in the kernel t is equal to 0. So this is the thing. So let lambda n be the sequence of real. It is a real eigenvalues with lambda n tending to 0. Okay, so now what we have to do is just to okay, En are the corresponding eigenspaces. And now the thing is like the finite dimensional case, no? So for example, En are orthogonal, is orthogonal to Em because of symmetry. So just the standard computation, which is T Un Um. On one hand, T is equal to lambda n Un Um. On the other hand, is equal to lambda m Un Um. And lambda n different than lambda n implies Um equal to 0. These are first year or computation. So the second is I take the set 0 is the kernel of T. So essentially what I want to say is that the kernel of T plus the other thing is the whole space, because what is left is nothing. So set F is the sum of all T's the span of all T's eigenspace. Okay? So are the eigenvectors here and the eigenvectors here, which a priori I don't know yet if 0 is an eigenvalue. Well, I don't know yet if 0 is an eigenvalue. I mean, it's not certain. Okay. Then let me see that T of F is contained in F, which is elementary because, well, F is a vector which is some component in En, and by definition Ten is lambda En, and then some component in the kernel which is mapped to 0. Okay? If V belongs to the orthogonal of, well, being continuous, I can close it to the closure. Then, what by definition I have, by symmetry, I have that 0. Well, it is again, I mean, just computation we already see, but let me do that again. Okay. It means that sorry, let's say U is F orthogonal. Okay, so this is what? Is equal to, by symmetry, to U TV. But this guy is inside F because I have that T of, wait a minute. Okay. I take V in F. So this guy is inside F. So this guy is 0. And then I get that the image of T of U is again equal to 0. So it means that T of F orthogonal is contained in F orthogonal. I think there are faster ways. So define, let's say 0, T restricted to F orthogonal, which is well defined. Now, so this is clearly symmetric. Well, is a restriction to a closer subspace. So it is symmetric and bounded. And what is the observation? The observation is that the spectrum of T is equal to 0. Because if exists lambda n, lambda, let's say T minus lambda, T0 minus lambda, okay, the kernel is not empty. Okay, let's look back. Then it belongs to one of these eigenvalues. 1 lambda n, and then contradiction. Now the proof is complete because, but then we know that T of F orthogonal is equal, so T0 is equal to 0. So F orthogonal is contained in E0, the kernel of T. And so I conclude that there is no orthogonal space to the span of these guys, which means that H is the Hilbert sum. So hence, let's say F orthogonal is equal to 0, and then H is the Hilbert sum of these eigenspaces. So the eigenspace is at 0 and the other one. So the conclusion, last part, let E and M be orthogonal bases such that, chosen such that, so E and M, okay, is a basis in A, E, M. That's the complete proof, in the sense that I have the sequence and I have built the thing. Okay, so this, with these results, we conclude the course. Now, so now we have to organize for the lectures. So I prepare some exercises here, and then we review everything from the beginning in some sense. And the exercises are taken from the book, of course. So they will represent more or less what you get in the written exam. But you may have some specific questions on some particular exercises, so you can contact me or you can ask it now, and let's see. Okay? So, are there questions on this last part of the lecture? Otherwise, we will start with doing exercises.
Yeah, we can move on.
Yep.
Professor, will you be sending us the sample problems that you
Yes, I didn't have
about?
time. I'm sorry. I didn't have time because of other duties. So yes, I will send you some sample and then you can try. I don't know if I can do it by tomorrow, but over the weekend, yes. But you can contact me later. So what I could do by today is just to prepare some exercises, but not write them down.
Okay.
Another thing is that the part that I presented in this course is the fundamental for functional analysis. So be prepared to review it whenever you go to sustain any application. Because this is something that can be asked very easily, and they require people to know it. So let's have some fun now. So let's review a little bit of Anne Banach. Okay, so what you need to know, or you need to remember, is that well, essentially, there are several things, but you can use that as extension of linear functionals from linear subspaces to the whole, okay, from linear subspace, let's say, it's clear. And the key point is that you need the function P, which is something like a semi-norm. So subadditive, if you remember, and P lambda x, positive homogeneous. Okay? So this is the control that you may require to hold. Because the extension, for example, a thing that I can ask, but this is, for example, so extension of linear functionals, but no requirement on continuity. So more precisely, let's say that, okay, this is something that comes to my mind now. So for example, let E, F contained in E is a linear subspace. And I'm asking, and then I have F from F to R linear. And I'm asking if there exists G extending F and G is linear. But I'm not asking about the continuity.
Yes, just we choose Gamel basis in the whole space E, and it's
What you do?
Hamel basis.
The
Normally
Hamel
in
base. Yeah, Hamel basis. Yes.
main thing is that for
So
any
you
vector
choose,
space there are Hamel bases.
an Hamel base which extend a Hamel base of F. Because you can, otherwise it's more complicated. So you take Hamel bases such that, let's say you have a sequence of X alpha, which is a base for the vector space, such that, okay, let's divide. So you take an Hamel base X beta, let's say X beta is, or X alpha is a Hamel base in F, and then you extend to, say, an Hamel base which is X alpha, and then you union, let's say, Y alpha or Y beta, and now is a Hamel base in E. So this is much easier, no? Because otherwise, then how to write, so this means that X in E is written like finitely many, let's say, C alpha X alpha plus, okay, D beta Y beta. And now what is the extension?
Gx.
So F X like.
No, Gx. J is extension.
Oh, yeah, sorry, yes, G.
Gx is just sum of C alpha, Fx alpha.
Yes.
And for other Y, we put, for example, 0 or 1.
Zero, yeah, zero is the easiest one. But you can do whatever you want.
Yes.
Zero is the easiest one. Okay, so this is the interesting requirement. Otherwise, it's just because, okay, you have the axiom of choice. Okay, and another thing to remember, and it's very important, you have the geometric form. Okay, So you have to set convex sets, and now because it is linear, you need to separate convex sets. And then you say that, for example, you have two cases, no? One when it is open, for example, and the other is one when one A, B closed. So let's say A closed and B compact. No?
We can generalize the first one. Namely, it's enough. A is an interior
minus
point.
B, they contain an open set in 0. Yes, but let's take this. You need to have that they contain an open set.
Yes.
So essentially here you have the separation. So let's say that there exists, so this is just separation, so exists F in the dual. So the important thing is that it is continuous. Okay, which such that F on A is less or equal than F on B. And in this case, okay, you can have that F of A is less than alpha for some alpha less than F on B. And what we have seen as an application of this guy, if you remember, is the duality of convex functions. Which is a convex function lower semi-continuous. So the proper, what is called proper, and different than plus infinity, and greater than minus infinity. So, and here we have the formula, which is it's phi star of F is the supremum of Fx minus phi x. There was also some formula when okay, the minimum, the min max, but this is something that was more an application. So this is very important. So this is called the Legendre transform.
Professor, I have a question about one of the exercise in the book is about Inf Convolution. So how will these things apply in the future?
The Inf Convolution?
Yes.
Okay. I didn't choose that because it was quite long, and okay, because it's a long. Well, it's not so long, but maybe you can contact me and then we work out. It is not strictly related. I mean, I cannot ask something about Inf Convolution because when this exercise is long, you prove that the Legendre transform is the sum, and then.
I think I can do it, but just what is the applications?
The application?
Yes.
The application is the regularization, no? So the application is that, well, you know the formula that the Inf convolution, so let's say phi Inf convolution psi star, okay, is equal to phi star plus psi star. Now, what is the Inf convolution? The Inf convolution is the infimum, so let's say phi psi evaluated in x is the infimum of phi x plus, sorry, phi y psi x minus y. Okay. Now let's assume, for example, that I take phi y, phi, let's say, phi of x is phi n, okay, or n times modulus of x. So let's look at this guy here. Or let's say psi, so I don't need to change. So this is what so first of all, what is the transform of this guy? The transform of this guy is psi star, so it's 0, so it's the characteristic function of the ball of radius r, n. So now let's look at this guy. So this guy is, if I give you x, I'm taking, and then I have a phi, which is given. So for each point y, I take the Lipschitz function, which starts at this point, and has slope n. Then I take the infimum of this guy, so I've discovered that essentially my function will be something which is the n Lipschitz. Okay, so this is my phi involuted psi. So it is a Lipschitz function, and by lower semi-continuity you can show that, okay, this is an application that I have in my mind, that phi, let's put an index n converge to phi as n tends, grows to phi, and tends to infinity. But this function is n Lipschitz, and I have the advantage of knowing what is the Inf convolution. So the Inf convolution is what? And so the phi psi n transformed is the transform of psi restricted, or time, or yes, restricted to the, okay, for f less than n, and then is plus infinity f greater than n. Okay, so what I did now is I found a family of more regular functions, which are Lipschitz, for which I can compute easily the Laplace transform. And, well, I have a nice convergence. So it is not convex. I'm sorry, I didn't do something convex, and that was my mistake. But, okay.
Okay.
This the application comes to my mind. So the only thing that I forgot to say is that this is non-convex. Just otherwise, the drawing in finite dimension is too easy. So keep in mind that the drawing should be much easier, but okay. Okay, so let's see an exercise that I prepare on this subject. Well, and then I just taken from the book. So E is normed. Have a finite set, or infinite set even, contained in E, and some real values. Then equivalent. So the first one is that there exists an f in the dual f xc equal to alpha e, or vice versa. Well, exists m. such that for all subset, and we can also ask to be finite.
I think we have discussed this during tutorial.
Ah, you did already?
I don't know.
Ah, yes, because I say it's the same at the end. Okay, so you know the solution. Beta I alpha I less or equal than m, the norm xi. Okay, so if you know the solution, is up to you. Who wants to talk to me? But since you have seen in the tutorial, should be easy and okay, so well, one has to answer.
Professor,
Yes.
I think the 2 implies 1 is harder, right?
So one
I
can.
think 1 implies 2 was.
1 implies 2. Okay, one can say 1 implies 2 and the other 2 implies 1.
Just writing this sum beta I alpha I equals to sum beta I multiplying what f h I. Just rewriting that. And that one, yes, sum beta I h I and
Yeah.
norm of f.
The opposite.
What?
So let's do the other. So who wants to be the guy? Okay, let's start with some suggestions. Suppose that the xi is a Hamel base, a vector base of E.
You define the functional to be the
If you
sum
have,
of
so
beta
you have,
I.
if you have seen the tutorial, did you have? Did you see it in the tutorial?
I don't think it was the same problem.
Yes,
There
because
is
there are several versions. No? One is
Yes.
in the primal space was in the dual space, and one is in the Ellis theorem that more or less. Okay, so what to do?
If it's what Gamel basis, then we can define function.
Yes. So define f of what?
At point x, f h a equals to alpha e.
So you define f of sum bi xi, which is one base, equal to the sum.
Sum of beta I alpha I.
Problem, is it well defined?
Yes, because it's Gamel basis. xi is Gamel basis, so it's well defined.
No, wait. Hamel basis, yes, it is well defined because you have, but I'm not saying that, but let's go back. So the assumption C, maybe this is not, this is even more than a Hamel base.
Okay.
So is it well defined? Okay, assume that x is the sum, is equal to the sum beta j xj. Two different things.
We subtract this.
So I want to say that this definition does not depend on the representation. Okay, then what I get, then the sum, this guy is equal to
0.
0, and then the sum is equal to 0. Because this guy is 0, and then I have that this guy is 0. And this guy, when I have chosen the beta, so beta I minus beta j, I get this observation. So I deduce that f is well defined.
Professor, I didn't understand the last part.
Okay, so here, so I suppose I have two representations.
Yes.
So it means that the difference is 0. So now let's use the assumption where the sequence beta I is, okay, beta I minus beta j. And apply the statement. The statement tells me that the sum of beta I alpha I minus the sum beta j fj less or equal than m the sum beta I xi minus beta j xj. But this norm is 0 because it's 0, the vector. So I deduce that the sum for I and for j is equal to 0. Is that okay now?
Okay, thank you.
So f is well defined. Now I need to prove that
Continuity is clear from that inequality.
yes, that is bounded.
Yes.
And f of the sum for any x as in the vector space. So it is equal to the sum for some beta I alpha I less or equal than m, which is equal to m norm of x. Okay, conclusion.
F is bounded and its norm less than 1, m less than m.
Yes, and however, in general, this is not a vector base for the space. So I just use the first statement, the extension, no? Final step. Extend f from
Set.
the span of the xi to E by Albana. Okay?
Yes.
Okay, and now there are some versions. So there is a version for, and now I have a question. Instead of giving the example, which is the Ellis Lemma, so let me say the thing, and then we just want to notice why is slightly different here. Normed, and then you have finitely many. So m greater than 0. And then you have finitely many fi is star. Then you have some alpha I in R, and then equivalent for all epsilon there exists x epsilon, the norm x epsilon less or equal than m plus epsilon, okay, less than m doesn't matter, and the value is equal to alpha I, and the same thing, sum beta I, alpha I, less or equal than m sum beta I fi for all, let's say, sequence beta I in R. So this is Ellis Lemma. And so the thing,
what is your question, Professor? What difference? What is the difference between these?
yes, if you, okay, the proof is more or less the same. Change a little bit. Okay, so you see the proof. I don't know. So the basic thing is that here we use the pre-dual. This is why the statement is done in this form. So even if I say this is alpha I, but then I want to have this is bounded, so you see the difference. In the dual, I get that I really obtain an M. So I obtain a point whose norm is exactly equal to M. But since now I'm the pre-dual, what I get is something which is, I need to enlarge a little bit. But this is the Ellis Lemma we saw in the lecture, and if you remember, was one of the key points for the Kakutani stuff. Okay. That's it. So was the weak start closure of the injection. So let's change. So this is a kind of exercise that can happen. So now this is about the first part, so the extension. Now let's see the geometric form, something about the geometric form. Now E, okay, a class of space that you need to know is just this one, C0, LP, and and just as a remark that you need to know and I suggest you to prove that C0 star is equal to L1, L1 star is equal to L infinity, and for P 1 to infinity, LP star is equal to L P prime with the convex the convex exponent. Okay, and L infinity star is a space which strictly contains L1, so it's non-reflexive. Another thing which is important is that C0 as embedded in L infinity is closed, but you don't have any topological supplement. So, but we didn't see this, but there does not exist a closed F such that F in L infinity, F intersection C0 is just the zero function, and F plus C0 is L infinity. So it's one of the cases that different from the Hilbert space. So recall here the Hilbert. Any closed subspace has what is called topological supplement. So let's say this is G, which is can be taken equal to the orthogonal subspace. So Hilbert space, and actually this is a characterization of Hilbert space. We know that if this is Banach, there is for sure something. So this is something that happens very often because it's the playground for all the theorems. So, well, there is some particularity of LP for p less than infinity, is that it has a, what is called a Schauder base. So you have a representation similar to the Hilbert, but now you know that the sum is controlled by some constant. So it's not that the norm squared is equal to the sum of the norm squared of the components. You have a constant in front. And this is something that does not happen always. But in any case, I strongly suggest you to digest these relations. These relations mainly. Okay, indeed the exercise is in L1 and LP. And now we have two closed sets. So, and here I require that in the sequence, so such that x, the even components is equal to 0. So essentially, if I have the representation, this is, I want n here. So 1 can be whatever, 2 is 0, whatever, 0, whatever, 0. Then y I define as n is equal to the sequences such that, so let's say sequence y such that, okay, is a sequence, and the even component is 2 to the minus n, the odd component, the previous odd component. Okay? So in my drawing, now y, well, whatever is here the value, the previous value, okay, the previous value is so twice, the first case is twice. So in the second case is 4 times, and I go on. Okay, let's just go on with the exercise, with the natural questions. RT space is closed.
Yes, close.
Why?
First one we can express as a intersection of closed sets.
Yes.
Intersection of hyperplanes. First one. Countably many intersection of.
Okay. Yes. The answer is indeed is that the pointwise evaluation which is from the sequence, I associate the point at n bar, so it is from LP. I go to R, is continuous. Is weakly continuous, is whatever, is continuous. Because it's a linear function, no?
Yes.
And then you see that these relations are, as observed by your colleague, these relations are just relations with, so compositions, or, well, this is just a counterimage, this is a composition of two continuous functions for each n, and then it is the intersection of closed sets. So the conditions are, okay, well, in this case are countably many. relations on pointwise evaluation. So this is the general reason why it is continuous, no? Because I have that is a, so it's for, or you can prove it directly, but I want you to understand that this is just the fact that the pointwise relation is continuous, then this relation is a continuous relation. So it's the inverse of this minus this is equal to 0, it's the inverse of a 0 of a closed set. Okay, so the easy one. So part 2, I say that x plus y closed is equal to L. Okay, I have a question. Well, we can see later. But for example, so they are closed, are they, what is the interior?
Interior?
Yeah.
Interior of some? What?
Interior of both of them.
Interior is
Then we can discuss the interior of some too. What is the interior of x and interior of y?
Interior is empty.
Empty. It's empty.
Strong interior. In strong
All
topology.
of them are empty. But this guy is more difficult to be proved.
Professor, how do we see that it's empty?
Okay, for this guy is more difficult to be proved because you proved, but we will see it later, why. In any case, let's consider for x. So if you take, so the relation, for example, x is contained in the set of sequences.
Or just x is contained by a hyperplane. And interior of any hyperplane is
yes. And this is what? This is the kernel of the linear functional of the continuous linear functional, which gives you the n, the 2n component. And we know that, so this linear functional is not 0. And then we know that this guy has empty interior. Or if you forget everything, you just observe that, okay, if x belongs to this point, then x plus, okay, epsilon, the vector which is 0, 0, 1 in the 2n component, 0, 0, okay, is, okay, does not belong to x, but it is as close as you want in the LP norm, whichever norm you want. Okay?
Okay, thank you, Professor.
So this is the direct proof. This is observing that, well, following the previous observation, that is just a pointwise evaluation. Okay, so to answer, then the same is for this one. To answer this guy, we will see later the why. So now let's go on and find the that x plus y is dense. Well, okay, from these two guys, I have that they are not dense. No, because it's the kernel of linear functionals, and the kernel of linear functional cannot be dense if the function is continuous.
And non-zero.
And non-zero,
yes.
And non-zero. So x plus y is dense in whatever is the space, E.
We take any z, for instance, for proving this fact, take any z in E, and consider finite first 2n coordinates of this.
Just prove that x plus y contains the set of finite sequences. Okay,
Yes, or
it's finite. Because we know that this guy is dense in all these spaces for p less than infinity. Forgot to say. For p infinity, this is false. Okay, so how to do that? Well, I just observed that, okay, let's see. Here, my degree of freedom are, here I have, so let's say, I want you to understand. So here, let's say I fixed the large number 2n, just to be correct. And then in x, so in y, once I assign the even component, the other are assigned. Okay? And the even components here are 0, so I need to solve that. So let's say I give z. I have that z 2n is equal to y 2n, because x 2n is equal to 0. And now I get that y 2n minus 1 is equal to 2n y 2n, z 2n. So I get what is the value. And now I have that, how to choose x. So I have x 2n minus 1 plus y 2n minus 1 should be equal to z 2n minus 1. I need to find two vectors. And then since everything is done, is x 2n minus 1 is equal to z 2n minus 1 plus minus, sorry, 2n y 2n. Okay, in particular, x plus y is not closed. Okay, I didn't state it, sorry. But in particular, the closure is E. So now the question is if it is the whole E. So what about this? So now I just want to draw your attention to this factor here. Okay, we are running out of time, so I want you to understand or give me the idea why is not dense in E, and also you can deduce that its interior is empty.
question is expressing this space.
I don't want to write the example that is not the whole E. I just want to say if you understand why is that so. Because I know that it's dense, and the next question, is it E or not? So the factor is, you see, every time I go back, I get 2 to the n, the previous one. So what would be now the thing? Okay, if I have a sequence which goes to 0, and so let's observe here. So for example, the sequence z equal to, okay, 2 to the, or let's say, z to n. So z to n minus 1 equal to 0, and z to n equal to 2 to the n half, to the minus n half. Okay, so clearly this belongs to any LP, but the inverse, because of this relation, I need that y to n minus 1 is equal to the n half. which does not belong to any E. Now, because the previous one is too large, when you move very far, the previous one grows too much. And you cannot control any norm, even if the Z goes to 0 exponentially fast. But this grows exponentially fast. Okay, so let's finish the exercise. So what about if there exists and so I have to close a space, the sum is not the whole, and then I'm saying that you can deduce from this one that the interior is empty. Because if the interior is not empty, this is a vector space, it is dense, and its translation is open. And so, and has the same radius, which is a contradiction. So, but let's go on with the thing, not this stuff. Just to finish. So the question now is, okay, so now I know from this guy, let's say this guy is Z bar, X minus Z bar, and Y are disjoint. Clearly they are disjoint because otherwise I have a vector in Y which is a vector in X minus Z bar, and then I get a contradiction. So the question is, can they be separated? Okay, the separation that I'm asking is not the strict separation. So I want an F different than 0, F different than 0, which separates them.
But we cannot apply both
Both?
versions.
No, indeed, the answer would be no.
What? They cannot.
So how to prove it? Okay, if such a F exists, so let's say, well, we can change a thing. So let's say for, I don't know which is better if, I think it's better like this, minus Z bar, just for easy, because one is a vector space. Then F on X should be equal to 0.
Yes.
Because X is linear. Well, also on the other, but just because it's easy. Then we deduce that F, so remember the duality, so Fx is equal to the sum Fn xn, and then we deduce that F of 2n minus 1 is equal to 0. Then we apply to the first. For y in y, then we have that f y is equal to the sum on the other one, which is over 2n of, of n, f of 2n, y to n. However, you see that this should have a sign. But, well, I can, if I give, so this should have a sign, and then you just take any y, which is, for example, 2n in the position 2n minus 1, or 2n alpha, and alpha in the position 2n. So it's get, for this particular thing, it is f2n alpha, and this should have a sign, which means that f2n equal to 0. So it's a contradiction. So I get that f is equal to 0, and then there is no separating hyperplane. Why is that so? Because in the formulation we have, none of them contains an open set.
And both of them doesn't compare.
And Both of them are convex, they satisfy the thing, but they are not, even their sum does not contain an open set. And so if you remember the proof, which was how to construct that row, which allows you to build the extension, and the row should be, or this function P should be equivalent to the norm is given by the gauge.
Minkowski function, I guess.
And the gauge, you have a gauge which is which is equivalent to the norm if you have a ball, if the set is, or the interior is not empty, or well, it's controlled by the norm.
Professor.
Yeah.
Why do we conclude f2n equals to 0 from f2n alpha? I didn't understand this part.
Here?
Yes.
Okay. Here are you okay? Because I can take x, and here I choose this particular point. So it is 0, let's say. I choose a vector in y, which is 0, 0 up to the 2n minus 1 position. Here it's alpha 2 to the n in the 2n minus 1 position, alpha in the 2n position, and then it's 0. This vector is in y. Then I just compute what is this scalar product.
Yes.
This duality product. So it's just for this, let's say this is n bar for some bar. This is f. So the previous one doesn't matter because it's 0. So it's just f2n bar times alpha. And now I have that this guy should have a sign for any alpha. Okay.
Why? Maybe I don't understand that.
Why?
Yes.
Because for any alpha in R, for any alpha in R, this is inside Y.
Oh, okay.
And then my request. So on the other, or more, if you want to go to the basic things, both of them are linear spaces, and then the F should be 0. I did the.
Okay.
Yes. Which
Thank
is
you.
a correct answer. I just do the computation. Okay, so we stop here. We see tomorrow, and okay, just ask me whatever you prefer for tomorrow, or let me know. If not, we go on. I think I'm going slowly. I'm sorry, but the exercise takes more time.
Professor, if you send us some of the samples, then we could maybe prepare for it.
Yeah, I know. I'm sorry. The time is limited even for me, so I can do whatever in 24 hours. I cannot do more.
Okay.
Yeah, but today maybe I will try to write down some samples.
Okay, thank you.
Okay, have a good day. See you tomorrow at 11.
Thank you, Professor.